ready to explore the integration of hardware-in-the-loop HiL technology into motorcycle models with Alessandro Baldari, HiL Sales Manager EMEA at VI Grade. In this presentation, Alessandro will explain how to add HiL to motorcycle models, focusing on ECU, radar, and brake-in-the-loop systems. Stay tuned as we uncover how this innovative approach enhances the testing and development of motorcycle technologies.
Let's start with, before talking about what, how, let's start by why. And start by why because there are some challenges in the motorcycle, as they are also for the automotive industries in the recent years. Some of the challenges are, for example, the new vehicle architectures, not only for motorcycle, as like sport motorcycle and touring, but also two-wheelers, new drivetrain and new platforms, even talking about hydrogen-powered motorcycles. Rider safety is a topic that nowadays is becoming more and more important. ADAS, no real riders want to be ridden on his motorcycle, but every rider knows it also is extremely boring to transferring on the highways, and in that case also during riding a motorcycle in a city environment and traffic, it's could be extremely useful to have an ADAS system supporting him. And then change of legislations, Euro 5 plus, it's a little bit more complex than Euro 5, but then maybe next year it will come Euro 6, and with a lot of constraints in terms of NVH, emissions. Motorcycles are becoming more and more complex in terms of software development, a number of ECUs, interconnections between ECUs and active systems, and then also NVH is becoming more and more important, as Giorgio highlighted before. So to do that, what is the vision? So we need to have a sort of platform. It is important to have a platform that can accompany the customer since the beginning and enables to integrate software in the loop, model in the loop systems from the early beginning till the end before releasing and validate a product. Our main aim is always to decrease the number of physical prototypes, not canceling them, but at least having the goal to reduce the number of physical prototypes and even reaching a virtual sign-off. And also take into account the effects and the interaction between control system ECUs while not having the physical motorcycle prototype yet, but start doing the integration before on a simulator or on a simulation station as well. And what is important is always to have the same real-time environment to integrate a model in the loop, software in the loop, hardware in the loop, and physical components. To do that, what we adopt in the automotive world, and then we are transferring also to the motorcycle, is the Auto-Hawk. Auto-Hawk is a platform. It's a real-time platform based on hardware and software. Is on the hardware side and software side, on the control part, is based on the concurrent real-time, is our sister company. It consists of a real-time system with a huge set of I/O boards in order to enable communication with the real physical ECUs or emulation of some components, even sensors. It's a Linux-based platform. And also is a flexible platform open to third-party software and application and possible to link to third-party also ecosystems. Three main application areas on the motorcycle development. One is the chassis. Everybody is familiar with VI Grade as a VI Real Time, as a software for motorcycle dynamics on the chassis. In that case, on the hardware in the loop side, we see application on dampers and brake and controllers. On the chassis side, ADAS and UX UI, the radar that are becoming standard for high-level premium vehicle motorcycles, but also cameras. There are companies already made patents on the cameras, stereo cameras applied on the motorcycles. Communication between vehicles, between motorcycle to cars, for ADAS application, and also HMI is an extremely important topic because it's also the interface between the driver, the road, and the ADAS equipment. And powertrain with all the shades of powertrain, traditional internal combustion engine, but also the electric powertrain and battery electric vehicles. The Autalk as a platform accompany the customers alongside the complete V-cycle, starting from offline simulation, keeping real time, where only model in the loop or software loop are available, doing the in-lab with the HiL system integrated into it with the first ECUs, prototype ECUs, or open ECUs, where you can run the software on that physical ECUs, together with connected with the test rigs, physical test rigs, where you have physical components connected, controller-based or not, where you can put your controller in a Simulink model. We start to think also onboard solution, as we did last year and we launched last year the Autalk onboard for automotive application. There's also something ongoing for the onboard solution. And then finally the digital twin, where you have the complete digitalization of your vehicle, and you can perform a lot of tests in parallel with the physical prototype. The enabler, the hardware side, we have for motorcycle application 2 main standard configuration of real-time platform. An 8-core system and 16-core system. For automotive application, we go also up to 64 cores, but we think that in terms also to keep the investment low, and the best compromise will be to play with those 2 systems. With the possibility also to expand with the expansion chassis. If you have a multiple I/O boards requirements, the system comes already with several slots available, PCI Express, but you can expand with the expansion chassis. And then Autalk X is a fully custom solution. The ecosystem is formed by hardware, the red part, where is the real-time system, the I/O boards. The I/O boards are predefined I/O boards like CAN, CAN-FD, Lean, but there can be programmable I/O boards like a programmable FPGA, together with different type of protocols. We are working on automotive Ethernet as well, that will become also standard in the motorcycle environment. We have then the simulation workbench is a middle layer where is used to convey all the inputs and outputs on the digital way and during the simulation. And then the ecosystem of software from VI grade with Drive Sim for managing riding simulators and bike real time. Simulation workbench is a platform made by concurrent real-time based on the Autalk hardware installed on the Linux system. And you can manage the real-time database, you can manage the programming, the testing, and the monitoring during the execution of the test. And this is really the main connection point also with the external devices like DSpace equipment, NI, Vector, and so on and so forth. The VI-grade ecosystem instead covers a larger variety of compatibility with third-party softwares, even third-party vehicle dynamics software or graphics. What is important that all stands and runs on the real-time system, and they are always compatible since the early beginning to the end. Now, the theory is fine. Let's go to some practice. Some use cases. Use cases about what we consider hardware in the loop. For us, it's a control system or mechanical test rigs connected to driving simulators. From the chassis, we have brake rig systems that are controllable from a HiL station, let's say a real-time simulation station, or from a riding simulator, let's say. The main applications are, of course, the analysis on brake system. We are talking about a full wet brake systems with the correct length of the system, the correct calibers, and so on, the correct ECUs mounted and implementing the control system. They can be also fixed by wire. You can have, if it's connected to a riding simulator, can be also analysis of the driver feeling, the brake feedback. Connected also to the control units of the ADAS, there can be the interconnection of all those control systems. Damper rig, all these systems are derived from automotive application. There will be the possibility soon after launch also to see some of those demos in the demo area. I don't want to spoil more of that, but there will be the occasion to see some of them functioning in the afternoon. The damper test rig, there is different specifications depending on the type of motorcycle and the applications. Here we see some in-depth specification in terms of performance. We are doing real-time simulation and testing of those dampers in real application cases as well. It can be replied applications or real-time driven application connected to a riding simulator. For complex system with several ECUs connected and physical components connected, here we see, for example, throttle bodies connected and ECUs, emulation of sensors, signal conditioning. All these are, say, typical application of pure hardware-in-the-loop systems. ADAS and HMI. Well, we know that ADAS systems are complex, and coming from automotive, it's interaction between a different control system, different sensors. Here I listed some of them. In ADAS, when you have a radar detecting, for example, a vehicle in front of you, you need to have an emergency brake system or the active cruise control. You will have the interaction between the sensor, the ECU of the sensor, and then the wheel speed sensor, the front and the rear, the suspension system, the most of the cases active suspension, the fuel injection ECUs, the IMU ECU, the ABS, and of course the ACC. And the HMI as well, because you need to send the signal feedback to the rider that is something's happening on the motorcycle. So you have all these interaction. How we do? You can test the physical components, or you can emulate the components by having a sensor model. In case of testing, we have the possibility, and you will see also a showcase here with the radar tester and the camera tester. So we have a radar rig, camera rig, able to make the sensor fusion between those two sensors, and together with the motorcycle model on bike real time, evaluate the behavior response of the dynamic of the motorcycle and also the control system. Main application of the ADAS coming from the automotive world is the primary application. You run offline simulation in real time because you want to train the ECU, you want to evaluate different use cases, different scenarios, strange scenarios that are most of the time also very dangerous to reproduce on the real world. With a simplified also driving simulator, what we call desktop simulator, and finally also we're connected to a riding simulator that Diego will talk to you about later. HMI, another big topic of discussion nowadays, how to create a simple interface that you can send back to the rider, simple information and what is happening on the motorcycle. The HMI are, because of the new TFT design, technology and so on, they are extremely crowded now. The same story as automotive, and now there is a trend how this HMI design can be evolved and go and say beyond the normal just populating with extra information, just popping up what is important to the rider. Final results and example is a complex system where we don't have a simple test rigs like a damper standalone, a brake standalone system, a camera and the radar standalone, but we're talking about like powertrain test rig, with you have the complete engine, internal combustion engine or electric powertrain connected to a rig, so sort of a powertrain test rig, and you can stress the powertrain connecting this test rig to a real-time motorcycle model, connected to the control system, so a network of control system with the HiL cabinets, connected to the software in the loop that can be developed in, for example, standing on a cluster, on a software in the loop cluster. Conclusions. So what I showed you here, some of these applications are real, are done already. Some of them are being under development coming from automotive. But what is important is all the hardware in loop applications since the early beginning, since the model in the loop mode are running in real time. This is what were most important things, that you never downscale the motorcycle model. You can go only up, you never down. Okay, this is very important. And also the fact that there are complex systems. You can exchange anytime. You can move from model in the loop to software in the loop to hardware in the loop. And anytime you can exchange. And there is also intercompatibility between departments. You know, the HMI departments, they can derive the motorcycle model and run, take it as a given, and then work on the HMI. And then the HMI department can give back the HMI development on the riding simulator guys, and they can see immediately the feedbacks while driving the vehicle, and then send back to the HiL systems to doing the control system, and so on. So, what is important, the last, let's say, key message is the AutoHawk is an environment, is a working environment, is a platform, is a real-time platform. That's it. Thank you.